Hello everyone, this is Monsieur Nadj.
Hi, folks. So here we go. We have the initial momentum, Pi equals mvi. The I is for initial. We have the future momentum right there. And to figure out the difference between these, so we would figure out the amount of change in momentum of a moving object, is for us to substitute this in here and this in here. The change in momentum is, as usual, Pf minus Pi. So after the substitutions, as you can see, it becomes this here right there. And then at this point, delta P, I'm going to pull the m as a common factor, just like you did in your math classes. And that would leave me with Vf minus Vi. Well, that's the change in the velocity. Therefore, the change in momentum is going to end up being m times delta V. Now at this point, I'm going to use another math knowledge that you have. I'm going to divide both sides by the same entity or quantity. In this case, I'm dividing both sides by delta t. Well, when you do that, we noticed in the kinematics labs that the change in the velocity over change in time is just the acceleration. Therefore, delta p over delta t, this quantity right here, will end up being equal to m times a. Now at this point, I'm going to multiply. This is a cool relationship to keep in mind because we're going to tie it to Newton's second law later. And then, now that we have that, we're going to multiply both sides by delta t. When we do that, notice how the delta t and delta t will cancel out, and we end up with delta p equals ma times delta t. At this point, we're going to do the same thing. Now, this is the story of changes. Changes in what? Changes in two quantities that were related to motion, momentum and kinetic energy. Okay, so now let's shift the attention to the kinetic energy. Well, kinetic energy is supposed to be half mv squared. If you're not sure where did this come from, go back to the the STR videos of Monsieur Nadj, so to see that the classical formula for kinetic energy is half mv squared. The subscript I and f are for the initial and the future, and then the change in kinetic energy is going to be kf minus ki, just like we did up there. We're going to be substituting. And now these two terms here are common, therefore we're going to pull this as a common factor. So we end up with Vf squared minus Vi squared. That's a little bit different from what you got there. So a different math trick is going to be used right now. You learned in your math classes that if you have a squared minus b squared, it's going to be factored into a minus b times a plus b. Except in this case, I have the Vf and the Vi as being my a and b. Good so far? At this point, the Vf minus Vi, my friends, is just the change in the velocity. And the Vf plus Vi divided by 2, okay, multiplied by this half, which is the same as divided by 2, is actually the average velocity. But wait a second. In the kinematics videos, again, you guys should have remembered, and in Labo 2 as well, that delta x over delta t, which is the change in the position over the change in time, is going to be equal to the average velocity. Therefore, in the end, delta k will be equal to m times delta v times delta x over delta t. Notice here, since this is a multiplication, I can put this delta t down here instead of there. If I do delta v over delta t, guess what? The a comes up again, the acceleration. Therefore, for this one, I'm going to get the change in the kinetic energy is equal to ma times delta t. I would like you please to ponder upon these two formulas now, because I am going to ask you to identify as many comparisons and contrasts between the two. Thank you very much. Monsieur Nadj signing off.